Welcome. For the few of you that were still sleeping, you should be awake now. Yeah, welcome, especially so early in the morning. Let's set me a timer because I'm really bad at timing. And debugging audio content with visuals. First thing first, who am I? I'm Maxime Coutant. I'm an audio software engineer. I work as a research and development engineer as part of the ADASP research group. It's an audio research group. You can check the website there. We make quite a few stuff, especially in deep learning. We've got a lot of PhD researchers. And it's part of the LTCI Public Research Laboratory in Recompile in France. Okay, so what are we actually going to talk about? I've been programming audio for 5 or 6 years now, and I've had a problem many times. It all starts with debuggers. Debuggers are one of the greatest tools you can use as a software engineer. It's for those who maybe never used it. It allows you to stop wherever you want in your program, and then you can verify the state, the variables of your program, and even modify them to verify if everything is going according to plan. But we do have a problem in audio is we technically are doing signal processing, so the data we work with is a signal. So it's usually composed of a lot of samples, and it's not easy to interpret. So often enough, what will happen is that you stop on a breakpoint, and you see great floating points value, and here, like, you got 9, you 10, it's fine. But what if you got dozens, hundreds, or maybe thousands, or 10 of thousands? I don't know for you, I can't read that. I can read the floating point value, but I can actually make sense out of it. Thankfully, a lot of really smart people before us already kind of solved this issue, because we already have like meaningful other representation for an audio signal. You could have simply plotting the waveform, so the amplitude over time, or you could have frequency representation, either spectrogram or the power spectral density. You could look, if your signal is a stereo, you could look at it at mid-side processing. If it's complex, you could look at the phase or the amplitude. But these representations are not always straightforward to get from a debugger perspective. Most languages, most debuggers does not come with a way to visualize this data. And it gets even worse with compile language, where to get these visualizations, you might need to instrument your code, so add code to your code to get these representations. And then you might need to recompile it, and maybe several times. So it creates a lot of friction simply in order to be able to interpret the data of your program. So because I've had this issue for several years, I'd like to present you a few tools that I discovered and tried these past years. The first one, it's not a tool strictly sensory, but it's simply adding code. So you instrument your code, you add in your code some way to write your audio data to your hard disk, then you run it, then you visualize the audio data in an audio data visualizer. So you might use a library that's made for it, like Libsound file or Juice built-ins. And one important thing is that some of you might not know, but for several audio formats like WAV, you could use floating point encoding. What that means is you could actually write to the file the exact floating point value you have in your program, rather than using which is usually a default, which is 16-bit integers, where you would lose data on the conversion. For example, integers cannot encode saturation, so value over 1, where floating points can. So run your program and then open up the Audacity or Sonic Visualizer. These are 2 great free tools. The third contender that I developed a few years ago, if you don't have access to a graphical environment, you can use Audai. So it's a TUI, so in a terminal way to visualize both the waveform and the spectrogram and the metadata of an audio file. Solution 2. Still solution 1. So it's a great solution because these tools are like really complete, really powerful. A lot of people use these, they're good. But it's like probably one of the worst solutions because you have to instrument your code. So you might need to recompile the code. You might even need to add a new dependency to your build system. And when the error is not when you think it is, then you have to instrument another part of your code and then another part of your code. So the trials and error strategy have a way bigger cost. And if you work with complex data, it's not always easy to encode these on files. Okay, so solution 2, and this one is for Python only, but it will get useful later. So Matplotlib and libbrowser. These are two big library, like two big major library. Matplotlib is a plotting library, and libbrowser is an audio processing library with a bit of plotting in it. And for those who don't know, when debugging Python, with most Python debuggers, you have access at debug time the Python interpreter itself. So you don't need to instrument your code. You can run code as it was in your program, but you don't need to add it. So you could simply type import matplotlib, pyplot. Oh, it's fixed. No. Oh, anyway, sorry. And so you can get this kind of visualization. So waveforms, spectrogram, the one we see before, these are from matplotlib. So really useful, really, really powerful. Really, like, it's probably one of the most used way to render audio data in the world. But it's for Python only, and not everyone uses Python, and might have conflicts in your environment, but usually it's fine. Okay, so solution 3, Sparklines. The Sparklines, the idea is to represent an app like a really reduced way, a really reduced vision of your waveform directly in your debugger. So the idea is to use pretty printers. A pretty printer is a way to nicely format a variable in your debugger output. So for example, a std vector is usually made out of a pointer and a size, but when you see the std vector in your debugger output, it does not give you the pointer and the size. You might see the point itself in the std vector. This is done using a pretty printer. So Sudaram had a really nice pretty printer for LLDB for Juice audio blog. So you can check the blog post where I explain how that works. And it looks like this on the bottom. You can easily identify zero values, zero crossing, none, or cycles in your waveform. Really useful, and the number of samples in your waveform. So that's great. It's integrated within LLDB, so you don't need to instrument your code. You just stop whenever you want. It's compatible with any ID as long as you use LLDB. You don't need to instrument your code, none, and zero crossing, great. But it's a bit low resolution because it has to use ASCII rendering, and nowadays we got big screens. It's a bit of a shame. It's compatible with Juice only. It's compatible with LLDB only. You cannot handle complex data if you ever work with, and you only have one representation available. It's the waveform. Okay, so solution 4. Solution 4 is trying to use an ID-like tool to get better integration. So I'm talking about mostly two extensions, one for VS Code, one for Visual Studio. They slightly differ, but are maintained by the same people, I think. It's called graphical debugging, and they're focused on 1D and 2D graphic rendering. So it looks like on the right, it opens up so you stop at debug time anywhere you want, so at runtime. And you say, okay, let me visualize this variable, and it will like draw a graph on a dedicated window in VS Code. It has a quite large language support, so C, C++, Python, C#, you name it. And honestly, it's really good. And if you don't want to use that, okay, so you don't see it, but there's a project called GDB Frontend. GDB Frontend is kind of similar, so it's a GDB GUI frontend which kind of have the same capabilities. So it supports a lot of different type from the ground up, and you can visualize to the vector, this kind of thing, like this. So this is great. I mean, it's directly integrated into your IDE, so almost no friction. You don't need to instrument your code. It in C++ it already supports Stud, like the STL and Boost. It supports different languages, and the users can add support for its own classes, and that's great. But you have to use VS Code or Visual Studio, and not everyone uses this. And it's very slow because it has to pass like every sample in the pretty output, and it's running in JavaScript. Like there's nothing wrong with JavaScript, simply it's slower. So if you have hundreds or thousands of samples, it can take like 20 seconds to plot a graph. That's too much. It has really limited language support. For example, C++ reference are not supported. And it's made for graphics. It's only support 1D and 2D data, and that's not exactly always the way we want to run the data. For example, if you have multi-channel data, you'd like to have your channel usually represented separately. You can do it. Okay, so from what we've saw so far, you might have understood I'm not exactly happy with all these tools. Don't get me wrong, they all save me a lot of times, and I do think they're all great projects, but they do not fit my need. And one day I was thinking about this great project a friend of mine showed me. It's called Jeff. It stands for GDB Enhanced Feature. And it's a GDB extension made for low-level development and reverse engineering. And it looks like what you get on the right. So here is how it looks on your terminal. And you can see the assembly, the source code, the stack, the register, all at the same time. Great tool. And I was thinking, well, if this is a GDB extension, does that mean that we can make extensions for debuggers? And it turns out, yes. Both GDB and LLDB, so the two biggest debuggers, both have a really powerful API, both C and Python. And the thing is, I know Python. Python is easy to develop with. It comes with the counter on most platforms. It's ugly but functional GUI module, and matplotlib that we saw earlier is in Python as well. So I was starting to think, we can do something here, and it's easily cross-platform. So we can do something probably good there. So today I'm happy to present my way of trying to solve this issue. Of course, there's no perfect solution, but we'll try to get there. Okay, so first, let's talk about what exactly we want to do, so we all know where we're going. So it's a hobby project. I'm doing this on my free time, so it should not take too much time because I need it when I'm programming. So I should choose the easiest path, not something fancy, something functional. It should be compatible with the most IDE possible because I don't like forcing the user to use a specific IDE, and I don't know what I might be working in the future. The same spirit, it should work with both LLDB and GDB. Same spirit, it should work with different languages, different frameworks, different libraries. It should be easy to install and remove because I don't want the user to have to make a lot of modification here and there, otherwise people simply won't use it. And the focus should be on audio and audio only. Nothing else, because if you try to get generic, then it easily becomes like really complicated to implement. Okay, so first thing first, when you start a project, you of course need a name and a logo. We all know that. So I'm happy to present Dave, which stands for the Debugger Audio Visualization Extension. Please don't start there. Okay, so I'll delve into a few details of the design of the tool, not too big details, simply for you to understand what we're dealing with. First, it will be in full Python. I will use little pieces of scripting to bind with GDB and LLDB. And for the GUI part, I will use custom tcounter, which is an overhaul of tcounter, and matplotlib. It should define the concept of an audio container in order to support a really wide variety of libraries language. And so an audio container should have like samples, a number of channels, number of samples, the sample type, the sample rate. And once you have an audio container, you should be able to render it in various ways, depending on what information you want to get out of it. You should be able to communicate with the extension using a set of debugger commands. Sorry. So for those of you who never used a debugger in the command line, you have commands for approximately everything, so continue, breakpoint, and stuff, and these are usually binded to the nice and fancy buttons you would get on an IDE when debugging directly from an IDE. And it should have two processes, or maybe more, but like little Python scripting running on the debugger process itself, and then all the things that we want to do shall run on another process that is the GUI process. That way we try to interfere as little as possible with the debugger. If you ever want to do that kind of stuff, for LLDB and GDB, there's this file called LLDB init and GDB init, and these allow you to make GDB and LLDB run code automatically when it starts. So you don't have to do anything once you modify this. One thing that I discovered during the project is that you have absolutely no guarantees on the debugger Python interpreter that will run your code. You have no guarantees on the version of the Python interpreter. You have no guarantees on which module will be available, so the environment. You also have no guarantees on which libraries were linked to the Python binary when compiled. So because of that, I had to split the code into two parts. First, the code that runs on the debugger, on which I can make almost no assumptions. So it should be pure vanilla code, pure vanilla Python code, like no complicated stuff, targeting 3.9 ideally, but usually use things that are robust and I've been there for a long time. And on the client, then I can make assumptions. So on the client, the GUI, I use an independent Python interpreter with its dedicated virtual environment running on Python 3.10 or higher. Quickly, if you've never used the debugger console within an IDE, here is a quick recap on how to find it. So you won't see it because it's on the bottom, sorry. On VS Code, you have the Debug Console tab on which you have to click, and then at the bottom you have a little entry when you can type comment. On CLion, it's over there. It's either called LLDB or GDB, depending on which debugger you're using. And on Xcode, it's at the bottom right as well. Okay, so quickly, what is the workflow with Dave? So imagine you stopped on a breakpoint. Then you see, you're saying, okay, I want to see what value is in my buffer variable. So you type your command Dave show my buffer. The Python scripting part get the samples, send it to GUI, and the GUI will print it. Okay, it's all 0. Then you reach a breakpoint, and Dave will deduce that it's a new context. Okay, you might want to see if the data has been updated. So it gets the samples, send it to the GUI, it's updated. Okay, so now that we know let's say how it's made, let's talk about what it can do. So it all starts with a command called Dave show and Dave delete. So Dave show is a command to say to GUI, okay, start and let me visualize this variable. If you don't want to visualize it anymore, you can either type Dave delete or use a dedicated button on the GUI. And the first time you type Dave show, it starts the process. So you pay for what you use. And then on each context change, so either a breakpoint or if you go up and down the stack, Dave will check which container is in scope. And for the container that are out of scope, it will signal the GUI, do not run these, we're not in scope, we should not be able to see these. And for the others, here is the new data. An important note is what I mean by scope. So for those of you who already used the display command in GDB and LLDB, it doesn't work like that. A display command, if you say display A, it will always show you whatever is in the variable named A. Even if the type change, it's not the same variable, who cares, it will show you. For Dave to consider that a variable is in scope, it requires two things. First, its name should be accessible within the context. And secondly, the variable hidden behind this name should have the same address as the one the first time. So you could have two variables with the same name tracked in Dave, but if they're located differently, they will be shown as two different containers, sorry. I talked a lot about GUI. Now, how does it look? So here is the window that Dave will start. It's composed of two tabs, the view tabs and the settings tabs. Let's talk about the view tabs first. So on the view tab, you have vertically stacked each container tab in scope and a graph for each channel in the container. So all is stacked vertically. And on the right, you have a little action box with a few buttons. We'll cover these in details after. Simply, there's the save button in blue, and this will allow you to save the data on your disk, so save the samples. You cannot see it, but on the bottom, you also have the matplotlib toolbar, and this allows you to navigate through the graph and to save the figures. So you could save the figures or the data. Now, the settings tab. So the settings tab is composed on the top of the global settings and then a frame of settings for each container that is in scope. On the global settings, you have the appearance, so dark light mode, and the default sample rate. And for each container. So let's dive a bit into that. So it always looks like this. On the left, you have the name of the container and the data layout. What I mean by data layout is you could use a std vector or floats to store stereo complex data, because this could be aliased. I don't know what you want to do with that. So if for some type of containers, you might do complex things. So the data layout is there to allow you to indicate, Dave, render this in this way. For example, if you use a juice or a shock and tell if buffer, you will not be able to edit the data layout because it's dictated by the container itself. And then you have this channel section. So first, the number of channel. It's editable if you forced a 2D layout on a 1D container. Then the switch for interleaved sample. Again, editable if you forced a 2D layout. And then a mid-side switch, which is editable only if you have 2 channels. So it will render mid and side rather than left and right. Then you have the view selector. So here it's selecting spectrogram. We'll see the different views later. And the view settings after. So here, for the spectrograms view, you have the size of the FFT, the size of the overlap, and the size of and the type of window. An important thing to note is that the type of layout will dictate what types of view are available. And then on the right, you have the sample rate of the container. So let's talk about views. So here are all the views that are available when you have real layout. By real, I mean like a scalar values, not complex. So you have the most basic one, which is the waveform rendering, which is simply plotting the amplitude and it's centered vertically on 0. Then you have the curve rendering, which is like the waveform, but it's not centered on 0 vertically. And you could apply log scale on both Y or X axis. And then you have the frequency representation with spectrogram and PSD, and both have the same parameters, so the size of the FFT, the overlap, the windowing. Then complex views. So it's quite simple. You could either choose to visualize the phase or the magnitude of your complex signal. Okay, a few more features. So let's get back to the view tab. So you got this concat switch, and the concat switch relates to the concatenate feature. So you have, it's an on-off feature enabled per container. You could either use the Dave concat command or the switch, it's equivalent. And when it's enabled, on each data update, what this will do is, rather than replacing the old data with the new data, it will concatenate the old data and the new data to a cell pan, and this will happen again and again. So if you iterate through time, for example, if you work with block size that are too small to get a meaningful spectrogram out of it, you might be interested to maybe accumulate a few blocks and then render the spectrogram. Freeze. Freeze is kind of like concatenate. So it's an on-off feature per container. You have a command, or you can use GUI. And what that will do is, when you activate the feature, it will freeze the current data on the graph. And on each update, it will show you the latest data and the frozen data. If, for some reason, for example, in the spectrogram case, 2 views are not superposable on a graph, then it will show you side by side. Last but not least, container support. So what kind of container can you use with it? So for now, it supports the basic 1D container of the STL, C pointers, C array, so std vectors, std span, std array. And any 2D nesting of these, so std arrays of pointer or pointers of span. And also the GSL span, so it's a Microsoft implementation, C++17 of span. It supports juice, audio block, and audio buffer classes. It supports all variations of chalk buffer classes. And for Python support, you can use NumPy 1D or 2D array. An important feature, you can add support for custom containers with a bit of Python scripting. So if you use a private framework or something that we do not support yet, that I do not support yet, you could do it by yourself. Okay, that's all for the features. A few final notes. Let's talk about OS. So Mac OS and Linux are supported. Mac OS, it's a bit tricky because I only own like really old Mac OS and I almost never used it. But technically, I'm pretty confident it should work now. Windows is an issue though, because the Visual Studio debugger that comes with Visual Studio, they does not seem to provide an API, or if there is an API, Microsoft is like really secret about it because there's absolutely no mention of it anywhere. And also, I had to use a bit of bash and VM shenanigans to like make it work to have the two independent interpreters. So I don't know how this will work in Windows, but probably it could be adapted. And most importantly, I barely use Windows and never used it for dev. But I'd be happy to help if someone wants to give it a try and make it work there. I know that you might be able to use GDB and VS Code, but that would require you to use the GNU compiler and not MSVC, so it might be tricky. About Python support, so I really wanted to support Python as a language as the others. But the thing is, most basic, like the basic Python debuggers, so PDB, the vanilla one, or DebugPy, the one of Microsoft that comes with VS Code, they both have, ironically, really limited Python API. You cannot do anything with it except that run and put breakpoints and stuff. So the support exists, but it's limited. You'll need to manually import dev command. You cannot do, like, there's no init file to do stuff automatically. You will have no automatic update and breakpoint. That might change in the future, but it's like really complicated. You have to rewrite a debugger class. And the installation procedure is a bit different, but the support is basically there. But it's not like a big drawback because you already have a really strong matplotlib support in Python. But installation requirement management, let's say, they will require you to have a Python 3.10 with both venv modules and tkinter modules working on your computer. For macOS, you can install tkinter quite easily. I provide a few help comments in the installation script. I provide an installation script. So it's a bash script that you can run. It will do every little configuration part for you, and it will install a CLI help command, so simply a command that you can call in your shell, and with 4 subcommands, so bind and unbind, to specifically bind and unbind Dave from one of your debuggers, Dave status to just check the version and which debuggers are binded, and uninstall if you want to get completely rid of Dave for any reason. What would be next? I'd like to support more languages and more frameworks. For example, have basic Rust support so that user can start adding maybe support for like custom framework in Rust. I don't really use it. And also again, SDK, you name it, like common framework that might be used to work with audio. I'd love to be able to integrate the concept of Sudara sparklines, but for every type of container. Since I already have a way to abstract a lot of different audio containers, it would be nice to use this to make a pretty printer out of it, so you have more features. Also, I haven't done unit test yet, because it's a complete nightmare to test. I have a UI to process, and it's like really different on each machine. So if you have feedback on how to test such a thing, I'd be really happy, because for now I have to test everything manually and it's a hassle. Also, audio playback could be a thing. If you ever work with blocks that are long enough to be listened to, it might be interesting. And actually, you tell me. I've been using it for a few months now. I started this in May, and I'm quite happy with it, but I don't have any real feedback on it. So if you think anything could be added, please let me know. A few thanks. So Mattis and Eyalame, who for the really pre-alpha testing, a lot of suggestion on where to get what were the priorities, and a big thanks to Chris Apple for tireless back and forth exchanges on how to make this work on the macOS jungle stuff. It was a nightmare, but it should work. Okay, should we try a live demo? Okay, so I got VS Code there. There's a current bug that I'm aware of with GDB on both VS Code and CLion. I'm talking with the devs of this. Hopefully we should get it working at some point, or in the meantime, you might want to use LLDB on CLion. Okay, so I got here, I might, want to Let me check. I might try to make it fit perfectly, since I'm a bit ahead of time. Okay, so there you should be able to see everything. So here is a really basic, we'll take a juice example. Here is a really basic juice code. I have audio block, audio buffer, and I simply fill values and stuff. So let's just start the debugger. So I use the fancy IDE debugger. See, I'm on the breakpoint, great. So I'm there, and then, well, I want to visualize audio buffer and audio block. So it's on VS Code, so you have to type exec to tell it to pass the command to the debugger and not to VS Code. And let's say, yeah, Dave show audio buffer. Boom, it's how the UI. Okay, I got these two, it's great, but I need the other one. Okay, we got mostly what we need. For example, you can see that it does not fit, so you can scroll if you want to see everything. Maybe the first one will concatenate and the other will not, and this is going to be spectrogram. Okay, let's configure it. Really small window because we have really small blocks. And this one is going to be mid-site rendering. Okay, so for now it's a spectrogram filled with 0 data, so it would not compute, so we simply do not compute and you'll get usually a warning somewhere. And now that is configured, let's continue. Next breakpoint. Here we simply filled the buffer with some values. So you can see it started there, and it indeed was filled with values. Okay, let's try to. Okay, then next breakpoint. Oh. And here you go. So it was filled, then it was filled with something. Channel 1 was not filled at first, and you got everything. And just, well, the program exit, dev exit, you're good. And I think that's all. So you can check for Dave. It's under GPL3, so you can use it for whatever private project you're doing. Simply cannot make a commercial product out of it. Here's the code. The slides are already available on Discord. You can, if you have questions or anything, you can create an issue. You can join me on Discord, on LinkedIn or whatever. Just ask me, but Discord would probably be the best. And thank you all for listening. And please tell me if you have any questions. Thanks ADC folks, especially tech folks and catering folks. They're doing the hard work. Thank you all.